I'm Chester Stubbs. I'm majoring in electrical engineering.
Hello, my name is Agustin Garcia. I'm majoring in electrical engineering.
Hello, I'm Jame. I'm majoring in electrical engineering.
And we are the Batteryless Energy Harvesting Team 2.
This is overall our product design, starting with the TEG, which will be connected to our boost converter to step up the voltage, which will be output from the bottom two wires, which the red and black wires. And on the right is the ADC ref and the ADC data connected to the microcontroller for data. And on the right is a humidity and temperature sensor.
This is our boost converter PCB board layout, which we're using to step up the initial input voltage coming in from our TEG. The step up voltage will be used to power our microcontroller and sensing devices. The input of the TEG will be coming in through these pins here on the left. And to the top of the board, we have our transformer that we are using to gather voltage for our ultra low power boost converter, which is located at the center of the board. To the right, we have our testing points to measure the critical points of our transformer and boost converter. And on the bottom right, we have our output pins to send data to our microcontroller. And lastly, at the bottom, we have our output of our boost converter, along with a supercapacitor used for reserve power. This
is our Bluetooth port. This 4 pin is to power our devices. The top 2 pin is to power our humidity and temperature sensor. And the bottom 2 pin is to power up the Bluetooth. This is the capacitor, and two pull-up resistor is required for the I2C connection. And the I2C bus will be communicating with the temperature and humidity sensor. In addition, it will be communicating with the Bluetooth too to send data to the receiver side. Lastly, we will add a UART connection to communicate with other devices if it is necessary. And there are some test points to help us to debug the board.
Shown here is our microcontroller board. It's programmed using a JTAG connector, which requires a resistor and capacitor. And in addition, 3 other capacitors are used for noise regulation and a clock regulator. The main board comes with 2 universal serial connection buses. One is used for this I2C connection, which then goes to the rest of our I2C bus. In addition, it's also used as a TX and RX input from another device. And in addition, we have an analog input bus. This bus goes straight to our ADC and allows us to read values from our soil capacitive sensor. This board is also designed to be powered using our TEG and boost converter.
Due to the miniature size of our components, we had to use this process to solder all of our components onto the printed circuit board. The paste will be applied to the respective pads, and after that we will use a vacuum suction to pick up the components and place them to each location. In addition, this helps us to stabilize the whole process with precision placement onto each location. Here we have our TEG providing the input voltage to our boost converter. On top we have water at room temperature, and on the bottom we have a heatsink to dissipate heat. And as you can see, we're receiving around 15 to 16 millivolts under these conditions. Under extreme conditions, we have our TEG in between an ice pack and a hairdryer blowing hot air. This creates a greater potential difference in temperature, allowing the TEG to provide a higher voltage output. We start here. This is our TEG inputting our connection, and with our ADC reference grounded, this is where our input is reading at 3.1 millivolts. Here is the input, and it's outputting here, coming out at boosting at 264.
Shown here is our I2C connection test using our custom microcontroller. We're using our Arduino to power the controller and a Raspberry Pi to visualize the I2C bus, shown on the screen. Shown here is our preliminary sensor array test. We connected our sensors using I2C through our MCU. Our MCU is then connected to our computer, which shows the output, humidity, and temperature on the screen. This system is powered using Arduino Uno, also fed through the PC. All connections are used with banana clips, and all information is routed through our MCU board.
On behalf of Batteryless Energy Harvesting Team 2,
We would like to extend our gratitude to Martin Family Foundation for sponsoring our research and Dr. Who to provide us expertise and guidance. Go Pokes!